My name is E, and welcome to the AI on Testosterone YouTube channel. In the first sequence of contents in this channel, we offer an introduction to differential geometry and functional analysis, which are one of the core mathematical frameworks that form the foundation of machine learning and quantum information theory. This is a knowledge tree that we will conquer in this episode. In this video, we will explore how smooth manifolds are constructed. Later in the series, we will see why this matters. In many areas of machine learning, the parameter space of a model naturally forms a smooth manifold, which the loss function becomes a smooth map on that manifold, and training a neural network is essentially a gradient flow evolving over this landscape. Let us begin by the most fundamental structure in mathematics, a topology. Suppose we have a set X. It could be a collection of points, a set of potatoes, or even a set of abstracted symbols. A topology on X is simply a distinguished collection of subsets of X satisfying three axioms. The first axiom is both empty set and the entire set are elements of this collection. Second axiom is the union of any families of set in this collection, no matter how large the family is, must also belong to this collection. And the last axiom is the intersection of finitely many sets in this collection must again be an element of this collection. A subset is called open exactly when it belongs to some chosen topology. In this foundational sense, openness is not the geometric notation. Actually, it simply reflects membership in the set terminology and nothing more. For example, a subset can be open on a topology and not being open with respect of another topology defined within the same set. In other words, a set equipped with a topology tells you which subsets are open, and those open sets determine the structure of the entire space. Thus, determining whether a subset is open always requires two pieces of information, the underlying set itself and the topology defined on it. The pair together are called topological space, and this space has no requirement for having any geometry nor coordinate. Now consider an example. If we take every possible subset of X, we obtain the full power set. This automatically forms a topology, known as a discrete topology. One can see that it satisfies all three principles easily. As a second example, let X being defined as follows, and consider the given candidate collection. Even though not every subset is included, it still satisfies the three axioms, and therefore it's indeed a topology. Now imagine we are given a bunch of points as entire set X. We define three subsets called U1, U2, and U3, which U1 includes X1 and X2, U2 includes X2, X3, and X4, U3 includes X4 and X5. Clearly, there are some intersection points. Now we would like to raise a question. If we are given any collection of subset of set X, can we always build a topology out of them? The answer is trivially yes. More precisely, any collection of subset of X can be extended to a topology by the following principle. We simply take those subsets, close them under all finite intersection, then close the resulted set under all arbitrary unions, and finally includes empty and the entire set itself. The resulted collection is the smallest topology containing all the three subsets which are open within this topological space. For the previously given configuration of U1, U2, and U3, one can easily verify the constructed member of the topology as follows. Note that for each sphere, only the red marked points are included in that set. The previous example raised the idea that the structure of a space can be controlled by a small collection of simple building blocks, i.e. a basis for a topology. A basis for a topology on X is a special collection of subsets satisfying two properties. First, the basis element must cover the entire space. It means every point of X lies in at least one of the basis elements. This ensures the space is fully described by this collection. Second, whenever two basis elements overlap at a point X, there must exist another basis element sitting entirely inside that overlap and containing that specific point X. In other words, this means the basis behaves consistently under zooming at any point in the space. Once a basis is specified, the topology it generates consists precisely of all unions, finite or infinite, of the basis elements. In other words, every open set in the space arises by assembling these fundamental building blocks. Actually, no additional structure is imposed. The entire topology is obtained by coherently gluing together the element of the basis. Building on the previous idea that a topology is fully determined by gluing together simple basis elements invites a deeper question. What kind of a space have a topology so well behaved that when we zoom in, they resemble familiar Euclidean space? The answer is one of the central objects in differential geometry theory called the topological manifold. A topological manifold is a topological space equipped with the dimension n and satisfying three structural properties. First, the space must be Hausdorff, meaning any two distinct points can be separated by disjoint open neighborhoods. The Hausdorff property requires only that two distinct points admit some pair of disjoint neighborhoods. It does not mean for all radius there must be a disjoint bulge. This visual intuition can be misleading. It may create the illusion that radius and distance are fundamental to the definition, but in fact they are not. Remember, neighborhoods do not need to resemble spheres, cube, pyramids, or any particular form. They are simply open sets determined by the topology defined. Second property says the space is required to be second countable, meaning it has a countable basis for its topology. This ties directly back to our previous idea. The topology must be generated by countable many basis elements. This property keeps the space manageable and avoids pathological behavior. Third, and most importantly, the space must be locally Euclidean, meaning every point has an open neighborhood that is homomorphic to an open subset of n-dimensional real space. In other words, even if the global shape is curved or complicated, each small patch looks exactly like a flat Euclidean space. Recall that homomorphism is a bijection, meaning it is both one-to-one and onto, and moreover its inverse map is also continuous. The previous discussed example is a topological space but not a topological manifold, because every open set in an n-dimensional real space contains uncountably many points. So if our space is countable, it simply does not have enough points to create those Euclidean-looking neighborhoods, and violating the third property. Thus, a countable space cannot be a topological manifold of dimension n greater than 0, because manifolds of positive dimension must have uncountable many points in every neighborhood. Combining all these three axioms, one can conclude that topological manifolds do not need any notation of distance or metric to be defined. Now that we have defined what a topological manifold is, let's look at one of the most iconic examples in geometry, the torus. At first glance, the torus might look like a complicated curved surface, a donut-shaped object living in three-dimensional space. But despite its shape, one can easily verify that torus satisfies all three defining properties of a topological two-dimensional manifold. Now that we understand what a topological manifold is, the next step is to describe how we assign a coordinate to it. This brings us to one of the core ideas of manifold theory. A chart on a manifold is simply a pair. Here, U is an open subset of manifold M and phi is a homomorphism from U to an open subset of n-dimensional real space. What this means is very intuitive. A chart gives us a local coordinate system, a way of describing each point P in U by an n-tuple in n-dimensional real space. These coordinates behave just like an ordinary Euclidean coordinate system, even though the manifold itself may be curved or globally complicated. Of course, a single chart rarely covers the entire manifold. Just as no single map can cover the entire Earth without distortion, no single coordinate system can describe a whole manifold. Instead, we use an atlas. An atlas is a collection of charts, whose open domains cover the entire manifold. Each chart handles a different region, and together they gave us a complete coordinate description of the entire topology. When two charts overlap, we need a consistent way to translate coordinate from one chart to another chart. This translation is captured by the transition map. The transition map takes the coordinate from chart alpha and expresses them in the coordinate system of chart beta. This is a map which is between open subset of n-dimensional real space, so even though the manifold itself may be curved, the coordinate changes takes place entirely inside Euclidean space. Now simply having a transition map is not enough. To do calculus on a manifold, such as to differentiate, integrate, or describe a vector fields, the coordinate changes must behave smoothly. Two charts are called smoothly compatible if their transition maps are infinitely differentiable. In other words, the coordinate changes is a C-infinity map, with all derivatives of all orders exist and are continuous. A smooth compatibility ensures that no matter which coordinate we use on the manifold, the underlying geometry remains differentiable. A smooth atlas is an atlas where every pair of charts is smoothly compatible. This means every coordinate system in the atlas agrees smoothly with every other one on their overlaps. A smooth atlas is what turns a topological manifold into a differentiable manifold, or i.e. a space where the calculus makes sense and where the smooth structure like vector fields, differential forms, and metrics can be defined. Now let us see what is the maximal smooth atlas. Starting with any smooth atlas, we can enlarge it by adding every chart that is smoothly compatible with the charts we already have. If an atlas already contains every chart that fits smoothly with it, then it's called maximal. A maximal smooth atlas represents the complete smooth structure of a manifold. Actually, it captures all possible coordinate systems that are consistent with the smooth geometry of that space. We now arrive at the central concept of this episode. A smooth manifold is simply a topological manifold equipped with the maximal atlas, whose transition maps are all C-infinity. This means that all coordinate systems on the manifold fit together smoothly, with infinitely differentiable changes of coordinate whenever charts are overlapping. In other words, a smooth manifold is a space where calculus works exactly the way it does in Euclidean space. To see these ideas in action, let's construct a smooth structure on one of the most important manifolds in mathematics and physics, the sphere. We'll start with the geometric definition of a sphere in three-dimensional real space. To build the charts, we remove first the North Pole, then the South Pole. This will give us two open sets, U subscript n and U subscript s. We will see that these two regions will cover the entire space. As a second step, we see that these open sets come from stereographic projection. Stereographic projection is a classical method for flattening the sphere onto the plane. Think of it as follows. From the North Pole, every point P on the sphere projected onto equatorial plane. This produces a coordinate map. Similar projection from the South Pole give a similar coordinate map. Both of these maps take the curved pieces of a sphere and flatten them into the regions in a two-dimensional real space. Each stereographic map and their inverse turn out to be a rational function with non-vanishing denominators on their domains. This means they are C-infinity. Thus both of these maps are actually smooth charts. On the overlap of these charts, a point represented by coordinate in the north chart transforms into coordinate in the south chart with the following transition map, which this map is again a smooth, rational function on its domain, so these charts are smooth compatible. Because the two stereographic charts cover the entire sphere and the transition map are C-infinity, together they form a smooth atlas. And since every other chart is smoothly compatible with these charts, it can be added to this atlas. And the sphere equipped with this atlas and defined stereographic chart is a smooth manifold. Thanks for watching this episode. This was E and you were watching the AI on Testosterone YouTube channel.